ฟิสิกส์นะเดี๋ยวผมก็เพิ่งลืมบอกไปนะครับเพิ่งพิมพ์เมื่อคืนนะครับnot balanced in yeah, that's the ionization state, right? Yeah, that's a different story. The mass number of the atom, which is denoted by M, okay, the capital M, is equal to the summation of the number of protons and neutrons in the nucleus locates some there, okay. M is above and Z is lower, okay, on the left side of this letter, okay. A hydrogen-like atom is an ionized atom that occupies only one electron, okay. It means that if you have something bigger than hydrogen, for example, helium has two. Oh, Streamlabs2YouTube. Oh. This one, check the microphone right now. Check 1, 2, 3. Check 1, 2, 3. Check 1, 2, 3. Okay. All right. So this is the section for M605, right? The yes, this one we alive at the we have to share the screen too, right? Yes, the radius expression, the pro-atomic radius, and we need to share. Fusion, but try. All right. Okay, the screen is all right. In yes, right here we arrive at the atomic radius, right, which is presented by the bow, right, Neil bow, and if there is something wrong. Yes. Oh. Okay. And you know that this is the expression. Oh, yeah. First, we have to be clear about this table, right? And as you know, the spin number, which is a kind of quantum number, is it is the unit of the spin is h/ here, right? You have ever seen the h/ before? H/ is this one. Is expressed in this one. You can see here in equation 32. I don't know whether anyone would like to join in Zoom or not. Right. นภัสนะครับนภัสอยู่ที่ YouTube นะครับ1 คนนะครับ and who else? Let me see whether anyone would want to join. There is no live version for this one, right? In Zoom channel. Anyway, we go here. Yeah, h/ is h divided by 2 pi. This one, right? It's the reduced Planck constant, right? You start from 6.6 times 10 to 34 joule second, and you just multiply it in terms of circumference, right? The distance around the circle, and pi is 3.14, and this term is something about 6.28, and you just divide, it's gonna remain 1.0 blah blah blah, and times 10 to negative 34, the same order, and the unit is the same, right? Because 2 pi has no unit. Yeah, h slash is the reduced Planck constant, and that's the unit of the spin number. And you know that once we say it's the spin number is 1/2, it means you have to multiply it by 1.05 Joule second. So it's times 10 to negative 34 Joule second. And that's the spin number, the total value of the spin number. But for simplicity, we would use quite often only 1/2, okay, and all these 3 subatomic particles would have the spin number as 1/2, 1/2, 1/2, okay. Okay, the result from this table, the table number 3, could be summarized as the following text. The number of protons in an atom is unique, okay. This is quite important, and that's the location here, okay. If you change this number, you're gonna have the different elements in the periodic table. The number of proton in the nucleus of the atom is equal to the atomic number, which is denoted by Z, okay. And Z is, it's integer, is a kind of integer. ถ้าแจ้งเพื่อนนะครับฟิสิกส์นะเดี๋ยวผมก็เพิ่งลืมบอกไปนะครับเพิ่งพิมพ์เมื่อคืนนะครับโอเคผมก็ลืมแจ้งคุณนะครับก็เลยไม่ได้ยุ่งกับอย่างอื่นนะครับต้องขอประทานอภัยด้วยนะครับโอเคyeah, the atomic number is denoted by Z, and in a neutron atom, the number of electrons is equal to the number of protons, and that's the stable, right? The number of positive charges is equal to the number of negative charges, right? And that's the stable condition. And once you remove the electron from an atom, okay, you're gonna have something which is not balanced. And that's the ionization state, right? That's a different story. The mass number of the atom, which is denoted by M, okay, the capital M, is equal to the summation of the number of protons and neutrons in the nucleus locates there, okay. M is above and Z is lower, okay, on the left side of this letter, okay. A hydrogen-like atom is an ionized atom that occupies only 1 electron, okay. It means that if you have something bigger than hydrogen, for example, helium has 2 protons, right? And if you throw away 1 electron from the orbits of helium, you're gonna have the same kind of atom as the hydrogen, okay, and that's the meaning of this sentence. When an atom has an atomic number set 1, 2, blah blah blah, and 3, so on, the term E square is denoted by Z E square. So what does that mean? For whatever you have, whether you have the radius, okay, E square is gonna replace it by ZE square, okay? Whether the radius or the energy, the three energies with its the potential energy, which is these where is that? Here, the potential energy, if you have E square, you just replace it by ZE square, okay? The potential energy, the total energy, or the kinetic energy, if you have E square, just replace it by ZE square. It's gonna be the same thing, okay? And that's the condition when you throw away a few electrons from their orbits. Where is that? Okay. So, for example, if we have the simple expression of minus 13.6, which is the conventional expression. Where is that? โอ้รูดเมาส์ไม่ค่อยสะดวกเลยนะครับ Okay, here the bar I don't know, it's Bow expression right here. If you have En, which is equal to 13.6 n divided by n square, that's the expression for the hydrogen atom, right? And เดี๋ยวผมขอมอนิเตอร์ที่เครื่องก่อนนะครับเพราะว่าเดี๋ยวมันเกิดเน็ตล่มอะไรขึ้นมานะครับthis term เน็ตล่มอะไรขึ้นมาครับโอ้ sorry ชวินพัฒน์โอเค Yes, so this one, right? This is Zoom, okay. Only Kitipan is there. Okay, only Kitipan is here. And who else? Okay, เรียบร้อยครับ yes once we start from equation number 27, which is the typical Bohr expression for the hydrogen atom, we need to extend these term for to cope with the bigger atom like helium, but you have to throw away a single electron from the helium atom. Or you have something like lithium or something like that, which is bigger than helium, the next element, right? Yeah, you have to throw away 2 electrons for the helium atom, or for the lithium atom. Periodic table. Okay, periodic table. Okay, let me bring you to the periodic table, right? This one. Yes, if you take a look at the periodic table, the first atom, the smallest one, is the hydrogen, right? Which is at this location, and you can see the atomic number, or the letter Z is number 1, the number of proton is 1, and the next element is helium, right? And yeah, the number of protons in the nucleus is 2, and you have 2 electrons, right? But in order to use that expression, you have to throw away a single electron from the orbit of helium. For the next one is the lithium. If you want to use that expression, lithium has the number of protons inside the nucleus as the number 3, right? There are 3 protons. You have to throw away 2 electrons from the orbits of the lithium. You're gonna get the same expression like a hydrogen. It's called hydrogen-like atom. Okay, the atom that has similar structure to hydrogen. Okay, and the next one is the beryllium, right? If you want to use the same expression developed by Niels Bohr, you have to throw away 3 electrons. Okay, so that the remaining number of remaining electrons is only 1, a single electron. Okay, and that's the way to cope with these new expression, equation 51. So what is inside equation 51? The energy at the end orbit, which is somehow like this. For the electron inside a bigger atom, it's called hydrogen-like atom. It's gonna be minus, okay, the same thing, negative 13.6 times z square. Okay, z square, z is the number 1, 2, 3, right? If your z is number 1, it means you use this expression to the hydrogen atom. But if you use or substitute z by number 2, you're gonna have the expression for lithium, right? The second element on the helium, the second element in on the periodic table here. Okay, next one, if you use z as number 3, okay, it means you are talking about the lithium atom. Okay, and if you use z as number 4, okay, 1, 2, 3, 4, you are using that formula for beryllium, which is this element. Okay, and so on, like the boron, carbon, nitrogen, oxygen. This one I forget about it, and neon. Okay, and yeah. Yes, the expression just have z squared, the atomic number, at the numerator here above 8 square. Okay, at the numerator, and the unit is the EV. Okay, please note that it's not joule second, it's only EV. All right, there are only 2 channels in the YouTube, and anyone who would like to join in Zoom, just let me know. Okay, ใครต้องการเข้ามาที่ Zoom ก็แจ้งผมนะครับ แต่ว่าหลักๆก็คือมี2 channel เนื่องจากว่า OBS ไม่ได้สตรีมนะครับเนื่องจากคอมพิวเตอร์ใช้รันงานyes so let's go for the energy level has been modified to this one, right, which is the result from 27. And for the Rydberg formula, this is the Bohr expression for energy level. We have more general expression for any atom which is bigger than hydrogen. The next one is the Rydberg condition, right? We start from the Rydberg condition in 31. It's 1 by lambda, and the Rydberg constant 1 by nf, the final state of the electron orbit, square, minus 1 by ni square, which is the initial orbit, right? You get the Rydberg constant, that's 1.09 times 10 to 7, and the unit is 1 by meter. But for the Rydberg formula, because this expression actually is derived from here, right? Rydberg condition is is this one, and you know that E square appears here, right? E square appear here, but E square times E square, so that we get E to 4, right? To the 4. E with the power of 4 means E square 2 times. So as we know, Z square, E square is is replaced by Z E square. So once we have E to 4, it should be Z square and E4, right? So yeah, that's why we have here Z square appears at after the Rydberg constant, and the remaining thing will be the same, which is 1 by f in f square minus 1 by ni square, 1 by lambda. And the next one is, the next quantity is the radius of the atom, okay? And you know, before the table number 3, there is an expression for the radius here, which is developed by Bohr again. In is 0.05 to 93 inch square, right? And the unit is nanometer. And once you go back to the original expression before you make the substitution of several constants, you could see E square at the denominator here, right? Whether with h/expression or the typical h, the Planck constant. You have the E square at the numerator. So, and according to our rule, wherever you see E square, you have to replace it by Z E square. So that's why we would have Z here at the denominator. And yes, that's the case here. You have Z at the denominator for the radius, and that's the Bohr atomic radius. But this one could be applied to the bigger atom like helium, lithium, beryllium, boron, carbon, nitrogen. Oh, I forget the F, the night, nine elements. F, what is that? Fluorine. Okay, fluoride. Yeah. Yes, that's the nine elements on the periodic table. You know, I'm from electrical engineering. I live every day. With electricity, so I would not have so much chance to look at the periodic table quite often. So that's why I sometimes forget the fluorine. Okay, the fluoride. Okay, let's get back to our lecture. Yeah, you have 3 expressions for 3 quantities: the energy level, the wavelength expression, and the radius of the atom. Okay, there are 3 quantities that could cope with the bigger atom. Okay, now we arrive at the first example about the bigger elements, right? For the bigger elements, we consider the helium. Okay, helium here. Let's get back to the to the table. You have here helium, which is the second element in the periodic table, right? And as you know, helium has 2 protons, 2 electrons, right? And once they say H with plus, okay, H with plus, it means the ionization version of the helium. Okay, because we have helium plus, we have helium and plus, it means 1 electron. Oh, sorry. one electron is missing. Okay, one electron is away from the helium atom. And once we say helium 2 plus, it means that 2 electron missing. Okay, this is S and this is R, right? Missing. So yeah, it means this is a proton, right? Proton of the helium, and you have 2 electron moving around the nucleus of helium, and you have another electron also moving around the nucleus of the helium. But we throw away, we use any kind of energy like electric energy or magnetic energy, magnetic force or electric force, and whatever you throw away, you move it out of the original orbit, so you would have only a single electron, and that's the condition we could apply this formula, right? En minus 13.6 z squared by n squared. That's the energy level. Okay, denoted by M. The helium, the ionized helium, has an electron in orbit denoted by n equal 1. When the atom is in its ground state, okay, it corresponds to n equal 1, and that's the quantum number as number 1. Find the energy in the ground state in electron volts. That's this expression, right? 51. And find the radius of the ground state orbit. So they asked us about this one. Okay, the 2 quantities only, 51 and 53, right? Yeah, let's start our computation. What is that? They want this one, right? The helium, right? And as you know, helium has 2 proton, right? Helium has 2 proton, but has 2 proton, 2 electron. Expression of 51, right? En, okay, equal to approximation minus 13.6 and z squared divided by n squared. And you know that we have to substitute z by 2 because this is the helium atom. It has 2 protons, which correspond to atomic number as number 2, and in the ground state is going to be the number 1, right? Yes. And yeah, let's substitute everything there. Then you will see minus 13.6 and 2 squared divided by number 1 square. Yeah, you just compute it, right? It's gonna be 13.6 times 4, right? Yeah, 54.4. So it's gonna be 54.4, and the unit is not joule, right? It's electron volt, and that's the first answer we could deliver, right? Let's check whether it's correct. Yeah. Oh, sorry for that. It's negative 2. Okay, minus 54.4 electron volt. And let's move to the second quantity, which is the radius. N equal to 0.0593 divided by z times n square above, okay, at the numerator. And of course, it's in the same way, we have to replace the atomic number by 2, right? Because this is the helium atom, and from the periodic table, it corresponds to Z. Here, Z equal to 2, right? Which is the helium atom, right? So Z is number 2, and N we consider the ground state, okay? Not only the detail of the which atom, right? Which orbit you are considering is also important, right? This one, n equal to 1, because we want to see something about the ground state. So it's 0.05293 n number 1 square divided by 2. So that's the number we're gonna put into the calculator, right? 5293. .0293, right? I'm not sure whether it's correct or not. Let me see. ขออนุญาตจำไม่ได้ yeah, 5293 divided by Z, which is number 2, right? Divided by 2. 2026465. Zero two. I forget. My brain is not good. 26465. 26465, and the radius is in nanometer, right? It's this one, and yeah, you can see that it's around 0.2 or 0.3 angstrom, right, which is 10 raised to negative 10, and that's the angstrom scale, right? And as I told you earlier, the atomic size is on the scale of angstrom, which is 10 to the negative 10. Yeah, and that's the case for the for 53, right? The radius, right? Yeah. So let's talk about lithium here. Oh, I didn't write down the solution to this one, right? Okay, let's consider the doubly ionized lithium. Doubly means we throw away 2 electrons for the lithium, right? Let's get back to the periodic table and let's find where the lithium locates. Okay, we start from helium. That's the single. That's the atom with single proton, single neutron, electron. The helium's with 2 protons and 2 electrons. The next one is lithium. Lithium is right here. Okay, lithium has three protons and 3 electrons, right? So when they say 3 doubly ionized, it means that we throw away 2 electrons from the lithium atom, the stable lithium atom, right? Okay, the stable atom would have the number of proton as the equal to the number of electron, right? So, but in the ionized state, we throw away electron, and in this case, doubly ionized. Double ionization means we throw away 2 electrons from the original atom of the lithium. So it means we are gonna have only 1 remaining electron in the orbit of the lithium. Okay, the nucleus is bigger, but still we have only a single electron around the nucleus. That's the double ionization, or the doubly ionized in this case, is excited to the first state. Okay, the electron is excited to, okay, it receives somehow the energy and it moves to the upper level. And where is that? So you have here proton, you have here another proton, and that's the nucleus of lithium. And you have one thing is that you have only a single electron around the nucleus of lithium, and this is the lithium 2+. And as I told you, 2+, it means we throw away 2 electrons from the original atom. Okay, and that's why we have 2+, because actually the stable lithium would have 3 electrons. So, right? Yeah. What does that mean? The first state, the first exciting state, it means this is the ground state. The ground state, and n equal to 1, right? And here is n equal to 2, and this is the first excited state. Okay, and that's the meaning. And that's the mean that when we are saying the first excited state, it does mean n equal to 1. Okay, we would say ground is the first one. Okay, ground is the first one, the first excited state, which is this is the non-normal state. Okay, it's equal to n equal number 2, right? It's the excited, the higher level, higher state from the ground state. Okay, that's called first excited state. Find the energy in the first excited state in electron volts. Okay, this is the unit EV, and here is the layers, right? Again, of the first excited state. Okay, the first excited, it means n equal to 2. Okay, let's go. Let's make the computation. So what we have to keep in mind in this scenario is that we are talking about the lithium 2+. We throw away 2 electrons to a electron are thrown away. Okay, are missing, you can say that. And first excited state. First excited state means that we have n equal to 2. Okay, and lithium atom means that Z equal to what? Which number? Okay, lithium is over here. It means the atomic number is 3. Okay, we have Z equal to 3, and yeah, let's get into the detail. They want to know the energy state E n equal minus 13.6 Z square divided by n square. Okay, and that's negative 13.6, and we have to substitute Z by 3 n by 2, so Z is 3 square 293, and Z times n square, right? And of course, in the same manner, we are gonna replace the Z by 3 n by 2, and yes, 0.05293, and n is number 2 square, right? Divided by Z, which is number 3. Yeah, let's compare it in calculator. ไม่ทราบว่าคุณเอาเครื่องคิดเลขเข้าห้องสอบมีปัญหากันหรือเปล่านะครับถ้ามีปัญหาก็แจ้งผมนะเขาไม่ให้คุณเข้าหรืออะไรอย่างเงี้ยเพราะว่าคุณถอดรูทยากๆคุณไม่สามารถถอดด้วยมือและในเวลาที่จำกัดผมคิดว่ามันไม่เหมาะสมที่จะไม่ให้คุณมีเครื่องคิดเลขในมือนะครับในการสอนครับโอเค 0.05 เดี๋ยวมีคนไหนจะเข้าที่ซูมหรือเปล่าเลยแจ้งผมนะเพราะว่าโอเค no one 0.05293 times 2 square divided by 3, right? So it's gonna remain, okay, of course the radius could not be negative. It's 0.0705773. The radius has units of nanometer. All right, and that's the case here. Radius in nanometer. All right, yeah. And now we arrive at the standard model of elementary particles. We are gonna visit these. We're gonna visit this table quite often, okay? And I would say that this table is not finished yet, actually, because there might be some particles happening in the physics could find. All right, yeah. Yes, how could we start? Okay, how could we start this one? ทำไมเสียงมันดังครับดังเกินรบกวนครับ Okay, yeah. Okay, we might visit this table quite often, and let's start with that. There are in many ways. Okay, if you take a graph view, this is the fermion, right? As I told you, this is the boson part. Okay, there are two main parts, fermion and boson. Okay, boson is something I don't know, something is still missing here. Okay, they might find something more in this side. Okay, because this is the current state. Okay, I could not, maybe I would die for my life, may not last until they would find something more. Okay, boson. Okay, boson comes from the word Bose. It's the surname of physics, and fermion is the surname of a physicist too, Fermat or something like that. I forget about why they call fermion. ปีที่แล้วยังแม่นๆอยู่เลยครับ แต่พอไม่ได้สอน fermion comes from okay, fermion I think it's yeah, you understand that model. From Fermi, yeah. Fermi is a famous physicist. Okay, his full name is this one. Okay, I would bring you. Oh no, I bring you to this person, fermion. Enrico Fermi. Okay, this is the famous oh no, this is famous physicist. Okay, here this person, Enrico Fermi. Okay, he lives in Italy. He makes many contributions in quantum physics. Okay, and another person is Michel Bose or something like that. No, physics. This person, yeah, Bose, Satyendra Nath Bose. He's an Indian guy. Okay, Indian physicist. Okay, yeah, boson comes from Bose. This person, he's quite intelligent. He studied only in India, and he found some thing in physics in the same generation as Albert Einstein, and he submitted his experimental result or his idea to a famous journal in physics at that time, but it was rejected. Okay, his work is not accepted, was not accepted at that time, and then he submitted he tried to contact Albert Einstein. He talked with Albert Einstein and something like that, and Einstein found that his idea is already good. Okay, so Einstein and Bose asked Einstein whether they could write the work or submit the work to the famous journal, the famous physics journal or not. Okay, and yeah, it's Einstein agree with that, and once they submit the work to the physics journal, it was successful. Okay, and after that, that's the beginning stage of Bose. Einstein invited Bose to work in Europe and so on, and I think Marie Curie too. Okay, has invited him to work with. Okay, and that's the origin why we say boson. Okay, Boson comes from the surname Boser, and fermion comes from the name Fermi. Okay, Fermi, sorry. Enrico Fermi, a famous physicist from Italy. Okay, he's Italian, and yeah, there are two parts fermion. Okay, whether it is violet or green. Okay, this part, the left hand side here, is called fermion, and from this side, it's called boson. Okay, it's called boson. And yeah, inside the fermion table, we have elementary fermions, okay, and this is the anti-fermions, okay. And in the first row of the elementary fermions, we have the lightest one, which is called up quark. Okay, this is the table of quark. Okay, in the it is represented by the violet here, and for the green one, it's not quite a little bit bigger size, bigger mass than up quark. It is 1.28. You could see the GE. Okay, G comes from giga, right? It's 10⁻⁹, and electron volt is what we have just learned, right? And C square is divided by the speed of the light. Okay, and yeah, that's the charm quark. And for the top quark, is a little bit bigger. It's 173. Okay, 173.1 giga again. Okay, the bigger side, the bigger mass, and that's the top quark. Please note that the quark has the quark here on the left side, which is not the antiparticle, which are not antiparticles, has the shard of 2/3. All of this has 2/3 shards. Okay, 2/3 shard of electron volt, of electron shard. Okay, 2/3 of 1.6 times 10⁻⁹ and for the antiparticle, the anti-up, okay, you have U, which is up quark. You have U bar, which is the anti-version of up, is denoted. Please note that the mass of the up quark and the anti-up quark are the same. You can see here 2.2 mega electron volt per c square, and the shard is different, and that's the point why we say anti-particle, because it has different, or the opposite side of the shard, which is -1 here, -2/3 of 1.6 times 10⁻⁹ coulomb, right? And that's the elementary shard by electron, right? But this is only 2/3. And for the spin number, they have the same spin number, 1/2, okay? And for the charm quark, it has there is antiparticle, which is called anti-charm. You could see that the mass of the charm fermion is charm quark is 1.28, and here is the same 1.28 for the mass of anti-charm quark. The difference is only the shard value, which is 2/3 for the charm quark and minus 2/3 for the anti-charm. Okay, the spin number is the same, 1/2, 1/2. Okay, and what about the top? Sorry for that, I forget to จะจบชั่วโมงอยู่แล้วผมลืมเปิดไฟให้ครับแล้วมันก็จะสะท้อนเนี่ยคุณจะดูได้ไงไม่รู้มันหลังแจ้งผมด้วยนะครับโอเควันนี้ก็จะลงในรายละเอียดของพวก standard elementary model นะครับอันนี้คือโมเดลนะครับที่นักฟิสิกส์คิดค้นไว้นะครับเป็น if you study chemistry you have a periodic table, right, like this one. Oh no, this one. You have you have the elementary table. That's the main thing for chemists, right? The people working in chemistry. But for us, once you leave, you work in physics, this is our table, the main table for us. This is the elementary table for the particle, right? In physics, okay? This is for physics. This is for, oh, I'm sorry for that. This is for chemistry, okay? This is the table for chemistry, the people working in chemistry. And here for us, the table for the people working in physics, okay? Let's get further into the detail. Yeah, the anti-top quark has the mass of 173 giga electron volt by c square, and it's denoted by the same way here, the letter T, but it has bar because we need to differentiate it from the top quark. This is the anti-top. It has the charge and minus 2 by 3. All right, and that's the antiparticle for the top quark. And for the down quark is a little bit bigger than up quark, right? What is the difference? Not only the mass, okay, down quark has more mass than up quark, but also the charge. The charge of down quark is different. It's not positive 2 by 3. You could see here. It's not positive 2 by 3. This is negative 1 by 3. And that's the main thing about the down quark. Okay, and the spin number is the same. Okay, spin property is 1 by 2 of the H slash, right? The unit of the spin number is H slash. And the next thing is the strange quark. Now we like the bigger element in strange quark has 96 mega electron volt per c square, and that's the mass for the strange quark. The charge is the same, minus 1 by 3, and spin number is 1 by 2. You could see that here that in this table, with these 3 elementary particles, they all have the charge as negative 1 by 3. These 3 elementary particles have the charge of 2 by 3, and here you have the antiparticles, which has the opposite charge to that. It's minus 2 by 3, minus 2 by 3. And here you have negative 1 by 3. And of course, you could guess that the opposite way to negative 1 by 3 is positive 1 by 3. And that's why we have here anti-down quark, anti-strange quark, anti-bottom quark, which have the charge of 1 by 3, 1 by 3, okay? So in summary, negative charge, positive charge, okay? The anti or the reverse version. Positive charge, you have negative charge here. And that's the quarks, okay? Even the quark, okay, physics file, it's difficult to detect it, okay? Yeah. Let's get into the leptons, okay? Leptons is what you may have already get used to because you know electron, right? You have ever heard electron before, okay? Electron is a kind of lepton, and physicists have found something like electron. It's called here in the forward way, it's called muon. Okay, muon is denoted by the letter mu. Muon is bigger than electron. You could see the mass of muon is 105. Most of these particles are not stable. Okay, the stable particle would be only electron. Okay, and muon is a bigger particle. It behaves like electron, but it's bigger. Okay, the mass of muon is 105. Okay, you could see it here, 0.51 mega electron volt. This is 100. This is now 200 bigger in size than electron, muon. Okay, but the charge of electron, of course, you know that the charge of electron, it's negative charge, right? Electron, and the unit is -1 because it's 1.6 times 10 raised to negative 19 coulomb, right? Again, muon, which is bigger version of electron, has the same charge value, which is -1. If you want to get it in terms of SI scale in coulomb, you have to multiply this value -1 by 1.6 times 10 to negative 19. Okay, you're gonna get the quantity in coulomb. And not only muon, the bigger particle than muon is known tau lepton. Okay, tau lepton has the mass of 1.77 giga electron volt. Okay, bigger than mega electron volt. Okay, this is like 1,007. Let's say 776 mega electron volt. This is 1,000. This is only 100. So this one is bigger version than muon, or even bigger than electron. Okay, so then please note that the charge of tau lepton is the same as electron and as muon. The spin number is the same. Okay, spin number. And let's move to the next one. To the right hand side, we're gonna have here the antiparticle section, and you know electron is negative particle, something similar to electron, but its charge is positive, not negative like electron. It's called positron. Okay, you know posi, right? Posi means positive. Okay, or positivity or something like that. So positron just follow from the word positive or something like that. Okay, it means it's like electron. The mass is the same as electron, 0.511 mega electron volt per c square. The spin number is the same, 1/2, but the charge of positron is not negative. The charge of the positron is positive. Okay, unlike electron has the charge of -1. Positron has the charge of +1, and of course, corresponding to the muon is a big version of the electron. It has the same charge as electron. It has the same spin number as electron. It's called anti-muon. Okay, this is the anti-particle of muon. It has the same mass as muon. It has the same positive charge as positron, or is the reverse version charge, or reverse charge version of muon. -1 here we have +1. And the spin number is not 1/2, it's 1/2 too, right? It's 1/2. And tau has also its own antiparticle. It has the same mass, but it has different charge. Okay, the opposite charge, which is +1. The spin number is the same. Okay, it's called tau, and bar is called anti-tau. Okay, the bigger version of electron, maybe some of you may have ever heard. It's called Electron Neutrino. Okay, Electron Neutrino. Please, let's get into detail of Electron Neutrino. It's denoted by nu with subscript E. And yeah, Electron Neutrino, what is that? It's a kind of particle. It's a kind of particle. It has no charge. Okay, there is no charge. You could see here the charge value is 0. The spin number is 1/2. And please note that this one is very, very small. You could see here electron has the mass of on the scale of mega electron volt, but this one has the mass of electron volt, simply electron volt, without prefix unit like mega, kilo, or anything. Okay, less than 2.2 electron volt. Before, the physicists believed that electron neutrino has no mass at all, but it's not the case. Someone argued that electron neutrino has a value of mass, but it's very, very small. It's very hard to detect. You could see here, the physicists cannot find the exact value of the mass of electron neutrino yet. That's why they say less than 2.2 eV per c square. Okay, because it's very, very light, very, very small. Is at the current state, okay, until at the moment we are living, human could not build a measurement device to detect the mass of electron neutrino. Okay, and yeah, let's get to the big version. Muon has also a zero charge version, which is called muon neutrino. Okay, muon neutrino has no charge. Okay, it corresponds to muon, but it has no charge. But the mass of muon neutrino is very, very small. Okay, less than muon. Is a little bit bigger than electron neutrino, but still physicists could not measure the mass of muon neutrino yet at the moment. Okay, maybe in the next 30 years or 40 years and so on, they could find the value of muon neutrino. Okay, the next one is tau neutrino. You know, tau is the big version of muon and electron. But the zero charge version of tau is called tau neutrino, and the charge value is 0. A spin number is 1/2. And yes, of course, once you have electron muon tau, electron neutrino, muon neutrino, tau neutrino, there would be also the positive, the anti-version, and it's called it's called electron antineutrino, which is the opposite version of this one. Okay, of course, this is not like electron positron. Electron has negative charge, so positron has the opposite way of charge, which is positive one. But here we start from electron neutrino that has no charge at all. Its charge is 0. Electron antineutrino has also no charge, but the mass is the same. Okay, the mass seems to be the same. The spin number is the same. We will see electron antineutrino later. We will see electron neutrino later in physics nuclear. Okay, and for the muon neutrino, we have also the muon antineutrino. For the tau neutrino, we have the tau antineutrino, and it's 19.2 mega electron volt per c square. 19.2 mega electron volt per c square. Okay, that's called tau neutrino. Okay, that's all about fermions. Okay, fermions come from the surname of Enrico Fermi. Okay, the Italian guy, this person, Enrico Fermi, this guy. Fermion come from his surname Fermi. All right, let's talk about. Let's move to the right hand side. Boson. Okay, boson, of course, as I told you, comes from the word Bose, the surname of this guy. He's from India, Satyendra Nath Bose. Okay, all of these have already passed away. Okay, he was born in 19 blah blah or 18 blah blah, and once the time goes by, he has already passed away. Okay, and that's a typical, right? Okay, the boson. Okay, boson is not so complicated as the fermion. Okay, boson could be classified into two types, roughly speaking. The first one is called scalar boson. This is what the world has just found, Higgs boson. Okay, Higgs come from the surname of this physicist, Higgs. Higgs boson. John Higgs. Okay. Oh no. Higgs boson. Yeah. Oh no, this is German. Higgs boson. The word Higgs comes from Professor Peter Higgs. Okay, Peter Higgs. Higgs boson was discovered by Peter Higgs from England. Actually, Peter Higgs, yeah. This person, okay, Peter Higgs from England, okay. He works in Switzerland he works in CERN, okay, ZERN CERN, which is a lab, the biggest lab in the world about elementary particles.